Hello, welcome back. The title of this lesson is called the mean absolute deviation and the standard deviation. This is part one. So in this lesson, we're going to focus on what we call the mean absolute deviation of a set of data points. We're going to understand how to calculate it and also, more importantly, what it means. And then we're also going to talk about the standard deviation and compare it and see how they're different. So it's a little easier to understand the mean absolute deviation. So we'll do that first. Then by the end of the lesson, you will also understand the standard deviation. These are critical to understanding any data set, any set of data points in math or in statistics, right? So I want you to think about a real life example. I want you to think about the grades in a classroom. The teacher gives an exam and some grades come in very high in the 90s and some grades come in low in the 70s, and there's a bunch of grades and the teacher finds the mean of those grades. Remember, I said statistics is all about two questions: the center of your data set and how spread out your data set is. So to find the mean is finding the center of the data set, and finding these deviations we're talking about, mean absolute deviation and standard deviation, tells you how spread out the data is about the mean. I'll say that again. These deviations here are telling us how spread our data is about the mean. So plus on the top side of the mean and minus on the bottom side of the mean is what we're interested in finding on average how spread out our data is out around that mean. So just to kind of illustrate the point here, let's take two situations. So let's say you take an exam and the teacher calculates that the average score for that exam is, let's call it 85. 85, right? So somewhere on a scale here is 85. That's the grade, right? And this is the average, right? Now, in order to have an average of 85, right? So somewhere over here is 100 and somewhere over here is less than 85. There's lots of different ways to get an average of 85. In fact, we're going to take two different scenarios right here. So we'll have another class where the average is, again, 85. So two different classes, and they both have an average of 85. But let's say the top class has some grades way out here, right? Lots of really high grades, some low ones, but lots of grades that are high, right? Let's say they even have a couple of 100s. Let's say they have, like 70 down here, and there's all the grades in between, but the grades are spread out pretty far about the mean, because the mean is 85 and we have some very low grades, and then we also have some very high grades. And when you average all of them together by adding them all up and then dividing by the number of students, you get an average of 85. Now here's a totally separate situation, a different situation. Let's say that in this situation, we still have a class average of 85, but we have a lot of students that are getting scores very close. In fact, there's a lot of duplicates right here. And they're all getting scores that are much, much closer and much more clustered close to 85. Do you see how in both cases you can still get an average score of 85? Because if I have grades that are very spread out about the center, I can add them up and divide and I'll still get an average of 85. But I can also have a second class where all of the grades are a lot more consistent. Maybe up here is like, 87, and over here or 88 maybe, or something like that. And then over here is like, 83 or something. But all of the grades kind of fit into this narrow range, and all of the grades here fit into a broader range. But in both cases, because the average value of anything is finding the middle of the data set, then you can still get the same average with totally different spreads of data. That's why I told you at the beginning that when we study statistics, we want to know the center of the data, but we also want to know how spread out the data is about the mean. Because here are two situations that have exactly the same mean, and if I only study the mean, then I don't have all the information because it's totally different situations. But if I know the mean and the deviation, or the spread, and if I know the mean and the deviation and the spread, then I know with a lot more clarity what's going on with the data. So here, the deviation is small about the mean. And here, the deviation is large about the mean. Deviation, the word deviate. To deviate means to depart from. So to have a high deviation means we must have data points far away from the mean, and to have a low deviation, we must have points very close to the mean, right? So here we're going to cover the first type of deviation called the mean absolute deviation. And then in a minute toward the end, I'll talk about the standard deviation. Actually, the standard deviation is what we use more often in actual statistics and math. But the mean absolute deviation is a little easier to understand, and it also is useful, so we'll start with that. First, let's pick apart the words, mean absolute deviation. Well, the word mean is there, and the word deviation is there. So what you're saying is you want to study how much the data points are deviating from the mean. But what does the word absolute have to do with it? What the word absolute means is that we're going to have some points that are lower than the mean, and you're going to have some points that are higher than the mean. When I say absolute deviation, I don't care if the point is lower or upper, in other words, below or above the mean. When I study absolutely how much it deviates, it just means I want to know how far the data is below and how far the data is above. In other words, being below the mean is almost like a negative number, and being above the mean is like a positive number. But I don't care about the sign. I don't care if it's plus or minus. I just want to know what the absolute deviation, either plus or minus, around the mean is. That's what mean absolute deviation means. It's taking the absolute deviation, either plus or minus, above or below the mean. That's all it is. So take a look at our first example. Here we have 8, 10, 6, and 12. Very simple, only 4 data points. And this data, let's have it represent the height of trees in my front yard. So one of my trees is 8 feet tall, another tree is 10 feet tall, another tree is 6 feet tall, and another tree is 12 feet tall. If we're going to study how this data varies about the mean, then we probably should calculate the mean first, and that is step number 1. So that is what we're going to do first. All right, so what we want to do is go down here and let's calculate the mean, right? So what we do is we say, here's the mean. You add up all these data points and then you divide by the number of data points you have. So what we have is the number 8 plus 10 plus 6 plus 12. It's 4 data points. We have to add them up first. That's why we put them in parentheses. And then after we add them up, we'll divide by 4 because there's 4 data points. So when you add 8 plus 10 is 18, then 6 and 12, what you're going to get is an answer of 36. You can see this is 18, 19, 20, and then 30, and then 6. If you add them up, you'll get 36, right? So you have 36, and then you'll divide that by 4. And when you take 36 and divide it by 4, let me switch color just to make it stand out a little bit. 36 divided by 4 is 9. So what we have figured out is that the mean, I need to kind of save a lot of board space because we'll be doing a lot of math here. The mean of this guy is 9. Now before we go any farther, let's first mark the data on the data set. We have one tree that is 8 feet tall, another tree that is 10 feet tall, and then we have another tree that is 6 feet tall, and then another tree that is 12 feet tall. So the data appears to me pretty evenly spaced out. It's, you know, and so on. So we have this data point here, these data points here, and we've calculated that the average height of these trees is actually 9, which makes sense because that's right in the middle of the data set. 2 points below, 2 points above. So we can then mark the mean on this graph here by putting a little dot right here. And we can say that the mean is equal to 9. The mean is equal to 9. All right, that's the center value, so to speak, of the data set. Now what we're interested in is not just knowing the mean. Remember, I just showed you a minute ago that there's 2 completely different situations involving grades that give you the same average. If you can have a clustered amount of grades, give you the same average as a very spread amount of grades. So what we need to do is somehow calculate how far apart each data point is from the mean. That's what we're trying to find, right? We're trying to see how far spread is the data about the mean. Is it all clustered very close to 9 in terms of the height of the trees? Or are the data points very far apart? And what we want to do is somehow figure that out. So what we have to do is go point by point and see how far is this point away from the mean? Okay, how far is this point away from the mean? And then how far is this point away from the mean? And then how is this far apart is that from the mean? So we can subtract and figure out how much deviation each of these points have from the mean just by subtraction. But then how do we roll it up into like one measurement of deviation? Notice the title of the lesson is mean absolute deviation. So what we're going to do is find those deviations and then calculate the average of them. Because we know this guy deviates or has a distance from the mean. And we know that this, and it's a larger number, right? And this has a distance from the mean. It's only a distance of 1. And this has a distance from the mean too. It's 1 away, but it's 1 below the average, right? And then this one is a distance as well, and it's 1, 2, 3, but it's again below. So we want to somehow average them all together so that we can find and take into account all of the deviations of all the points, but also roll it up into one number, so we'll just average the deviations. That's why it's called the mean average deviation. All right, so what we need to do next is find something called the deviations. And it's going to look difficult at first, but I promise you're going to get the hang of it pretty fast. Right? What we have to do first is let's look at this first point, 12. What we want to do is figure out how far away is it from the mean. So we have to take 12 minus 9. So we have to take 12 minus 9. But because we're going to be subtracting where we're taking 6 minus 9 and 8 minus 9, we're going to get negative numbers later on for some of the data points, for half of the data points. And we don't want to use negative numbers for our deviation. We want the absolute deviation, which means the absolute value. So instead of just putting 12 minus 9, wrap it in absolute value, which means what we're going to do is we're going to get the absolute, what comes in here? 12 minus 9 is 3. Positive 3. And when we take the absolute value of 3, we just get 3. So the absolute deviation between 9 and 12 is just 3 because it's 3 units higher. Okay? Let's take the next point, 10. So we want to see how far away 10 is from 9. And we're going to put an absolute value sign around it. 10 minus 9 is 1, and we take the absolute value of 1, and we get a 1. So that means this point has an absolute deviation, which is 1 unit away from 9. The absolute deviation of this point is 3 units away from 9. You see, all we're doing is find how far apart each point is from the mean. Now, what do we do when the points are lower than the mean? So we're going to go over there, here, and do that now. So you're taking the point minus the mean. The point minus the mean. Here, 8 is the point, so we have to take 8 minus the mean, which is 9. But we have an issue here. How do you start with 8 and you take away 9? Well, we're going to put absolute value around it. 8 minus 9 is just asking yourself, if you start at 8 on the number line and you go backwards 9 units, then if you go back 8 units, you get to 0. But if you go back 1 more unit, you'll get to negative 1. So 8 minus 9 is negative 1. But when you take the absolute value of negative 1, you're just going to get 1. So what it's telling you is that the absolute difference between the distance here is just 1. That's what I was telling you in words earlier. All I want to know is how far apart these points are from the mean. These were positive distances, so we just had positive numbers to give us positive absolute values. But these, because they're below, we get here when we take 8 minus 9, we get a negative 1, which just tells us it's 1 unit below the mean. But I want to get rid of all the signs and just find out how far away it is from the mean absolutely. So I get a value because of the absolute value of negative 1. This point is 6, so 6 minus 9. What you have to ask yourself is how many units is there? And the difference between 9 and 6 is 3, but since you start with the smaller number, it's really going to be negative 3, and you're going to have an absolute value around it, and then take the absolute value of negative 3, you get a positive 3. What is this telling you? It's telling you is that the number 6 is 3 distance units away from 9. That's all it's saying. When you really start with 6, and then you take away 9 from it, like we did here, 6 minus 9, you would start at 6 on the number line and count backwards 9 units. You would get to 0, and but you have to go 3 more units, so you would get to negative 3. So 6 minus 9 is negative 3. But I don't want the negative sign. I just want to know how far away it is absolutely, either above or below the mean. So the absolute value just gets rid of the sign for me altogether. And this tells me the bottom line piece of information. This point of 12 is 3 units away from 9. This point of 10 is 1 unit away from 9. This point of 8 is also 1 unit away from 9, and this point of 6 is also 3 units away from 9. When you subtract with the bottom numbers, you're going to get negative numbers, but we use the absolute value to get rid of it. That's why it's the mean absolute deviation. And then the numbers on the other side are already positive anyway. So now we know how far away these points are from the mean. All right? So then next we're going to calculate the mean absolute deviation. We call it MAD, mean absolute deviation. This is the deviation of one point, the deviation of another point, the deviation of another point, and another point, how far away from the mean they are. To find an average of how far our points differ from the mean, we just average them, we add them up, and then we divide. So what we do is we say we have a deviation of 3, a deviation of 1, another absolute deviation of 1, and another absolute deviation of 3. Notice they're all positive numbers here. We add them all up and we have to divide by 4 because there's 4 of these deviations. We're averaging them. That's all we're doing. So we have 4, and this is 4, which gives you 8 altogether. Okay? And when you have 8 there and divide it by 4, you get 2. Okay? So I'll just put over here that the MAD equals 2. So what this is telling us, the mean absolute deviation, when you say it's equal to 2, is it's telling you that if you know the mean of your data, which is the center of your data set, and you know the mean average deviation is 2, what it's telling you is on average, most of your data points are going to be within 2 minus the mean and 2 plus the mean. Because how did you arrive at this number? You found the deviation of all of the data points separately and how far apart they are from the mean. And then you took all those deviations and you just averaged them to get an average value. So this average value just means that if we know where the mean is, then most of your data will be plus 2 units above the mean and minus 2 units below the mean. It's a mean average deviation because remember, half of the points were below the mean and half of the other points were above. So when we get a mean average deviation of 2, it means that within plus or within minus 2 of the mean, we should have the majority of our data. So the way you would represent this visually, and I hope I don't run out of space here, is 2 above the mean is 11 and 2 below the mean is 7. So if I come over here and do something like this, between 7 and 11, we can say that the MAD is equal to 2, right? Which means that minus 2 this direction and plus 2 this direction. So what it's saying is that most of your data points are going to fit within this boundary here, right? Now, in this particular case, we only had 4 data points. So 2 of them fit within this region here of plus or minus 2 about the mean. And then we had some data points that are, of course, outliers, a little bit outside of that window. But when we get to a further problem with more data points, then you will see a little more clearly that the mean absolute deviation is telling you, on average, how far plus or minus the mean most of your data lies. And why is this important? Because if I just give you, like if you have all the data, then you already know everything. But if you don't have all the data, if I just tell you, hey, here are the grades for the exam. The grade is 80. Well, that doesn't tell you anything. It doesn't tell you if everybody got close to 80 or if lots of people got 100 and lots of people got like 60, right? It doesn't tell you the information that you really want to know, which is how did the kids really do? So, but if I tell you, okay, the mean was 80, but the mean absolute deviation was 5, then that would tell you that most of the kids got plus or minus 5 around the mean, meaning all the way up to 85 and all the way down to 75, plus or minus 5 points about the mean. That's what the MAD is telling you. It's telling you most of your data points, not all of them, but because it's an average, right? But most of your data is going to fit between plus or minus that distance about the mean. Now, what I think I would like to do is I would like to solve probably the next problem. And then once we get the next problem and go through the MAD calculation again, I'm going to come back and I'm going to show you how to calculate something a little different called the standard deviation. It's very similar to what we've done here, but I think it's going to be clearer if we just do one more example before we back up and show you how to use this information to find the standard deviation. All right, so let's go over here and take a look at this data right here. So this is the age of when someone had their first child, right? So here's a 20-year-old that had a first child. Here's an 18-year-old that has a first child, 22-year-old, 21-year-old, 19-year-old. Here's an outlier, somebody who extremely young had their first child, okay? So let's first of all see what this data actually looks like. One 20-year-old had their first child. One 18-year-old had their first child. One 14-year-old, again, extreme outlier having their first child. One 22-year-old had their first child. A 21-year-old had their first child, and then finally a 19-year-old had the first child. So I think you can see from this data that most of the data that we've collected are way over here having their first child. But there is an outlier over here, right? So of course I could ask you, what is the range of this data? And you could say 22 minus 14, you would get a number that would be the range of the data. You could say, what's the interquartile range? There's different flavors of expressing how broad your data is. But most of the time, we want to know what is the mean of the data set and what is the standard, or I should say the mean absolute deviation or the standard deviation of the points plus or minus about the mean, right? So the very first thing that we want to do is we want to calculate the mean of this data set. So let's go over here and find the mean, right? How do we find the mean? We're going to add up all these numbers together. So we have 14, then we have 18, which is right here. Then we have 19, then we have 20, then we have 21, then we have 22. So 14, 18, 19, 20, 21, 22. 1, 2, 3, 4, 5, 6 data points. We take and then we divide. We add them all up first, then we divide by 6. And you're going to get 114 divided by 6. And what you get at the end of that, because all this comes out to 114, you divide that by 6, you're going to get 19. So what you figured out is the mean, which is the average of all of these data points, is equal to 19. And it kind of makes sense because here is 19, right? Here is the mean, right? And I have some points above the mean and some points below the mean. And the reason, if you ignore your outlier, if you just cover it up, the mean would be 20 because that would be right in the middle. But because I have this outlier, it's pulling my mean down a little bit because I have one extreme outlier so far to the left. But this is the mean of the data set, right at 19 right there, okay? Now we want to figure out how far away each of these points are about the mean. That's what we want to find out. So we want to basically do by subtraction, figure out how far is 22 away from this, how far is 21 away from this, and so on. So let's go and do that. Let's find the deviations. Right, the deviations. All right, so let's start off with the highest, 22 minus 19. We have 22 minus 19. We always wrap it in an absolute value. Right? So 22 minus 19 is going to be 3. Absolute value of 3 is just 3. Okay? Next point, 21 minus 19. That's going to be 2. We have a 2 here, but then the absolute value of 2 is just 2. All right? Let's go over here and say, next we have, let's see, that was 21. Let's do 20. So we have 20 minus 19. We get a difference of 1, and we take the absolute value, and we get a 1. So this is just telling me how far away each of these points are away from 19, right? Now what about, we do have a data point exactly at 19. So we have to include that one too. So we're going to take 19 minus 19, and we get 0. That makes sense because the deviation of this point from the mean is just nothing. It's on top of the point itself, so it's 0. And then we have to look here at 18. Now we take the point minus the mean. 18 minus 19. And your mind explodes for a second and say, how do I do that? Well, when you subtract a big number from a small number, all you do is you flip it around, do the subtraction normally, and if it's small number minus big number, you just put a negative sign on it. So just like 19 minus 18 is 1, 18 minus 19 is negative 1. And when you take the absolute value of that, you get 1. All it's saying is that this point 18 is 1 unit below 19. But when I take the absolute value, all I want to know is how far absolutely it is. It's 1 unit away. And then finally, I have this one over here at 14. So I take 14 minus 19, and same sort of thing. If you can't do it, just flip it around. 19 minus 14 is 5, but this is not going to work, so you just make it negative 5. Because what happens is if you start at 14 and you go 19 units backwards, then you're going to land on negative 5. And when you take the absolute value, you just get a positive 5, like this. So our absolute deviations are 1, 2, 3, then 5, 1, and 0. Those are our, I shouldn't say mean absolute, those are our absolute deviations. Now let's calculate the MAD, which is the mean absolute deviation. So here are the deviations, the absolute deviations of all the points and how far they are from the mean. So all we have to do to figure this out is we just add them up and we divide, right? So what we're going to have here is, we can start over here, 5, 1, 0. So we can have 5 plus 1 plus 0. Then we have 1, 2, 3, plus 1 plus 2 plus 3. And we have to divide by 6 because there's 6 of these deviations, right? So we have 6 here, and then 7, and then 8, 9, and then 10, 11, 12. So we have 12 divided by 6, which is equal to 2. So what we figured out is the mean absolute deviation here, again, is equal to 2. It's just a total coincidence that that's what it was in the other problem as well, but it's equal to 2. This means that on average, these data points, on average, the bulk of them will be within plus 2 units on the top side of the mean and minus 2 units on the bottom side of the mean. 2 units away on the top is 21, and 2 units away on the bottom is 17. So let me just check myself real quick. I'll go from 17 all the way to 21 right here. And what this says is that the MAD is equal to 2. That's 2 units above the mean and 2 units below the mean. So if I tell you, here is, some ages, and the mean was 19 and the mean absolute deviation was 2, then you would know in your mind immediately that the center point of the data was where I told you it was 19, and most of the data would fall between plus or 2 units on either side of the mean. And you can see that 1, 2, 3, 4 of the 6 data points do fit within plus or minus 2 units of the mean. And the reason it works out that way is not magic. The reason it works out that way is because we literally calculated how far away each point was, and then we averaged them all together. So therefore, the data must mostly fall within that range, okay? Now what I want to do, we do have more problems, but what I want to do next is I want to calculate something related to this. Here what we've done is we calculated the mean average deviation. Notice that we use these absolute value signs. We didn't want plus and minus numbers because we're going to average them. And if we average plus numbers with minus numbers, then we'll often get 0, and then you can't calculate anything. So half of these data points are below the mean and half are above. So you're going to get negative numbers like we got here when we subtract them, right? So if we just add them up and average, it's not going to work. So we take the absolute value first. There is another way to get rid of the negative signs. Here we had -5 and -1, and that is to square the numbers, right? Because when you square -1 times -1, you're going to get a +1. And when you square a -5 times a -5, you're going to get a +25. So another way of looking at that, if you're not sure about the negative number part of it, is what we can do is we can square all of these numbers here. Let me go back over to this problem here. So I think what I'm going to do is erase this little part because we already know that the MAD is equal to 2. And the other thing I would say before we get started is if you don't really know how to square a number, how to multiply negative numbers, or we'll do a square root in a second. If you don't know what a square root is, then just skip this part. I think the most important thing is the mean absolute deviation. This is, I don't want to say it's bonus, but it's almost bonus, okay? So let's talk about the standard. I'll put STD as standard deviation. Okay, all we do is we take all of these deviations that we got, the 1, the 3, the 1, the 3, and we square them. So let's take this 1 squared plus 3 squared from here, and we square this one, 3 squared, and we square this one, 1 squared. And what do we get when we square everything? This is a 1, this is a 9, 3 times 3 is 9. So it's 1 plus 9 plus, what is this, 9 also. And then what is this, 1 squared is just 1. So what you have is 10 plus 10 is 20, right? So you have 20. I guess I should put it over here, 20. So when we square all of the deviations, we get 20. Now what we did actually is we squared them all and we added them all up, I should say. Instead of just adding them, we square them first and then we add them, and then we're going to divide that by 1, 2, 3, 4. We're going to average them just like before. And 20 divided by 4 is 5. Now what we've done is instead of just taking the absolute value, we squared the numbers. Then we averaged them. And when we get an average value, you might think you're done, but the problem is you've already squared everything. So if we were talking about, this is like I can't remember what our example was. If it was let's see, what was it exactly? The height of the trees. This is height of trees, right? Well, we calculate the deviations, then we square it. So if the height was in feet, then the units are feet squared. And then it doesn't mean as much. So at the end, what we do is after we've averaged everything together, we just take the square root of 5. And when you take the square root of 5, you get 2.23. So this is the standard deviation. Notice that the mean absolute deviation we got was just 2, and the standard deviation that we got was 2.23. So they're just different flavors of measuring how far the data is about the mean. The mean absolute deviation says that most of the data falls between plus or minus 2 about the mean. The standard deviation says most of the data falls a little bit wider, between plus or minus 2.23 about the mean. And the standard deviation is more what we actually use in real statistics down the road, usually. I mean, we have a use for the mean absolute as well. But this, I wanted to put them in right next to each other so you could see how they're calculated. So you take these deviations, you square them. That also retains and gives you positive numbers, right? And then you add them up. And well, you average them essentially. You add them up, you square them first, then you average them by adding them up and dividing by 4. But then you have to take the square root because you squared everything. In order to have the correct units, you square root it, which is the opposite of squaring it. And that gives you 2.23. Again, it's very close to what we got from the mean absolute deviation. All right, so let's do the same little exercise over here, the standard deviation. So we have all of these deviations that we've calculated, 1, 2, 3, 0, 1, 5. Those are the distances from the mean. Let's square them all and then average them instead of just averaging them like we did here. So what we will have is we will have 3 squared. Let me go in the same order. We'll have 5 squared plus 1 squared plus 0 squared here plus 1 squared plus 2 squared plus 3 squared, right? And let's continue down here. This is going to be 25 plus 1 plus 0 plus 1 plus 2 times 2 is 4, and 3 times 3 is 9. All right? So what do we get when we add all this up? Here we have 1 plus 9 is 10, and then we have plus 25 is 35, and then this 5 is going to be 40. So what we're going to get when we add up all the squares is 40. But we're trying to average them, right? We square and then we add them all up. Then we have to divide by 1, 2, 3, 4, 5, 6. So we have 40. We divide it by 6. And we have 40 divided by 6. We get 6.66. Now you would think you're done because you've averaged. But the problem is you've squared all the numbers. So what we were talking about here was the age of when you have your first child. But when you find the deviations and then you square, because the age is in years, when you square it, your units are wrong. So once you do all the averaging, you then finally take the 6.66 and you take the square root of that. And you take the square root of, and you get 2.58. And this is the standard deviation. Standard deviation. 2.58. Notice the standard deviation that we calculated, or the MAD that we calculated before, was 2. So we said that most of the data would fall between plus or minus 2 of the mean. When we do a very similar calculation, the standard deviation is 2.58. That would be somewhere over here, plus 2.58 about the mean, and minus 2.58 about the mean. It's just a slightly different calculation. It's actually used a little more often. The only difference is when we found the mean absolute deviation, first we find the deviations, we add them up, divide by 6 to get the average. An alternative way, called the standard deviation, is to square the deviations first and then average them. So we add them up and we divide by the number, same as before. But to get the units correct, we have to take the square root to undo the squaring we did, and we get a number that's very, very close. The mean absolute deviation and the standard deviation should always be pretty close. All right, let's take a look at problem number 3. All right, here we have, let's say, the age of children when they first get braces. So let's take a look at the data. First child gets their braces at 13 years old. Another child gets their braces at 15 years old. Another child gets their braces at 17. Another child gets their braces at 16. Another child gets their braces at 14. So it looks like we're all over the place right here, okay? So the first thing we're going to do is we're going to calculate the mean. We're going to calculate the mean. So how do we do that? We add up all these numbers and divide, right? So if we have 13 plus 14 plus 15 plus 16 plus 17, we add them all up and then we divide by 1, 2, 3, 4, 5. We have to divide by 5. Okay? And when you add them all up, you're going to get 75 divided by 5. And when you take 75 divided by 5, you're going to get 15. Right? So the average, or the mean, is 15. That makes sense because that's right in the middle of the data set, right? So we can go ahead and put a little dot right here, and we can say that this is the mean, right? They're right in the middle of the data set, okay? Now let's go calculate the deviations, which means how far apart each of these points really are from the mean. Let's start with 17. We have 17 minus 15. We're going to wrap it in an absolute value. This is 2. When we take the absolute value, we're just going to get a 2. That's 2 distance units away from the mean. Then we have 16. 16 minus 15. That gives you 1. And when you take the absolute value, it's 1. So that's going to be 1 distance unit away from the mean. All right, let's go over here. We have a data point right on top of 15. So it's 15, which is the data point, minus the mean, which is 15, which is 0, and the absolute value of 0 is 0. This just means this point is 0 distance units from the mean. Next, you have 14 minus 15. Now this is going to give you negative 1. You can't really do the subtraction, so in your mind, flip it around, make it 15 minus 14, and slap a negative sign. And so it's going to be, I guess I'll put it down below, positive 1. This means that this is 1 distance unit away from 15, but of course, it's 1 distance unit below. Next, we have 13 minus 15. Same thing. You can't really subtract it, so in your mind, make it 15 minus 13, which is 2, and since you can't really do it, you just make it negative 2, take that absolute value, and it becomes a 2. So we're doing a little bit of subtracting to get negative numbers here, right? You can't really do the subtraction, so if you start at 14 and you go down 15 units, you must go down to negative 1. If you start at 13 and you go down 15 units, you must land on negative 2. Once we take the absolute values, we get rid of the signs. So now we know the absolute deviations. Let's find what we call the MAD, the mean of these absolute deviations. So we need to add them all up, right? So what we're going to have is a 2 plus a 1 plus a 0, which is here, plus a 1 plus a 2. And we're going to divide it by 1, 2, 3, 4, 5, because there's 5 of these deviations. All we're doing is we're averaging the deviations. So what we're going to have here, this is going to be a 3, 4, 5, 6. So it's going to be 6 divided by 5. And when you run 6 divided by 5, either by hand or through a calculator, you're going to get 1.2. So the mean absolute deviation is 1.2. So if I go over to my chart, what does this actually mean? If this is 1 distance unit, and this is 1.5, 1.2 distance units above is going to be somewhere right around here. Somewhere right around here, right? And it's going to be over here, right? So like, you could put a little mark right here, and you could put a little mark right here, and you could say this and this. It's got to be 1.2 distance units away, right? So this is 16.2. And this is 13.8, right? Because all we did is we're basically saying is that the MAD is equal to 1.2. That means that most, quote unquote, most of your data is going to fall between plus 1.2 and minus 1.2 about the mean. So if we start at the mean and we go 1.2 units up, that's 16.2. And if we go down 1.2 units, that's 13.8. So most of the data is going to fit between 13.8 and 16.2. And we actually do have 3 of the 5 data points that do fit in that boundary there. So if I tell you that the mean of these ages and there is 15, and their mean absolute deviation is 1.2, then it gives you an idea where the center of the data is and how spread apart the data is, plus or minus 1.2 about the mean. Same thing here. When the MAD was 2, I just went 2 units up and 2 units down. This is the first time where the mean absolute deviation is a decimal here, all right? So I think what I'd like to do before moving on to the last problem is just really quickly calculate the standard deviation from this. And we expect it to be something pretty close to 1.2. All we're going to do is square these deviations and then average them. That's all we're going to basically do. So for the standard deviation, right? All we're going to do is we're going to square them all, right? So let's start here. 2, so it's going to be 2 squared. This is going to be 1 squared. This is going to be 0 squared. And then 1 and then 2. So we have 1 squared, 2 squared, right? So what are we going to get when we do that? We're going to have, this is 4, this is 5, because 1 squared is 1. So this is 4, this is 5, this is 6, and then 6 plus this is 4 is 10. So we're going to get a 10 right here. Make sure you understand, 2 squared and 2 squared is 4, that's 8, and then there's 9, 10. This does nothing. So we're averaging them, right? We add them up, we got a 10, and then we average by dividing by 1, 2, 3, 4, 5, which is 2. So we average them, but the problem is since we squared everything, we kind of messed up the units a little bit. So we take our average at the end and we just take the square root of it, which is 1.41 standard deviation. Notice the mean absolute deviation was 1.2. The standard deviation is 1.41. They're pretty close. So all it means is, depending on which measure of spread you're using, it's either going to be plus or minus 1.2, or if we use standard deviation, it'll be plus or minus 1.4, which will be a little bit farther out. And we would just say most of the data falls in that range. I do have one more I want to work really quickly, so let's take this down and I'll work one more and we'll wrap it up for mean absolute deviation and standard deviation. All right, here we have our last problem. This is the temperature in degrees Celsius on a given day. So one day it's 8 degrees, 4 degrees, 13 degrees Celsius, very cold days in general. So let's take a look and see what the data looks like. One day we measure 8 Celsius, another day we measure 4 Celsius, another day 13 Celsius, another day 15 Celsius, another day 12 Celsius, another day 11 Celsius. Let me just double check that I got that correct. Now, let's find the mean, and then after that, we'll consider how far apart these points are above or below plus or minus the mean. So, first thing to do is to write down the mean. How do we calculate the mean? We just add up all these numbers and divide, right? So, it's going to be 4 plus 8 plus 11 plus 12 plus 13 plus 15. We add them all up, then we divide by 1, 2, 3, 4, 5, 6. Okay? So when we add these up, okay, we're going to get 63, and we still have to divide by 6. So the mean, when we do all this stuff, when we take 63 and divide by 6, we're going to get 10.5. You can do long division on that or run it through a calculator, you're going to get 10.5. Now what does this actually mean? We go over here to 10. Here's 10 and 11. 10.5 is right in the middle, and we're just going to say this is the mean. Now, some of this data is going to be above the mean. You see, most of it actually is. Some of this data is below the mean. You see, we have fewer points, but they're farther apart. That's why it pulled the mean down a little bit. So the mean, nevertheless, is at 10.5. Now, what is going to be the mean absolute deviation? Let's calculate how far apart each point is from the mean, and then average them all. And that's going to be the mean absolute deviation. So, first, let's find these deviations. I'll just put DEV for deviation. All right, let's start over here with 15. We have 15 minus the mean, which is 10.5. Right, we're going to put an absolute value there. So 15 minus 10.5 works out to 4.5. Take the absolute value, it's still 4.5. Let's take a look at the next problem. The next point, 13 minus 10.5. When we take 13 and subtract 10.5, we get 2.5. Take the absolute value, we still get 2.5. Right? That was this point. Now let's take 12. So it's 12 minus 10.5. Right? So it's 12 minus 10.5. We get 1.5. Take the absolute value, we still get 1.5. Right? Now what about the point 11? So we have 11 minus 10.5. That's positive 0.5, which we take the absolute value, we still get a positive 0.5. Right? Finally, we're at the points that are below. We have to start with 8 and subtract 10.5. We want to wrap an absolute value around it because we know we're going to get a negative number. You can't really start with 8 watermelons and take 10.5 away. Well, you can. You're just going to be left with a negative number. So just in your mind, flip it 10.5 minus 8, and what you're going to get is 2.5, but it's a negative 2.5 because it's backwards like this and you don't have enough. So negative 2.5, and we take the absolute value, we just get 2.5, like this. And from our last point is the number 4, and so we take 4 minus 10.5. Again, you can't really do that subtraction, so flip it around. 10.5 minus 4 is 6.5, but it's backwards, so make it negative 6.5. Wrap it in the absolute value, we get 6.5 is the answer. So what we basically figured out is that all 6 of these points, we know how far away they are from the mean. Now, some of them we got negative numbers. That just meant they were below the mean. But when we take the absolute value, it's just telling us how many units, absolute units it is, even though it's negative, how many units it is away from the mean. Now, once we have these deviations, we calculate the MAD, right? So what we have to do to find the MAD is we have to add them all up. We start with 6.5 right there. and we add to it 2.5 from that deviation. And then here we had 0.5, and then we had 1.5, and then we had 2.5, and then we had 4.5. Okay, and once we get all of that, we get an answer of 18. But we have to divide by 1, 2, 3, 4, 5, 6. We have to divide by 6 because we're averaging, which means we have 3. So the MAD, or the mean absolute deviation, was 3 in this case. So what does this actually mean? This means that 3 distance units above and 3 distance units below, we expect most of our data to be. So 1 distance unit, 2, 3 is at 13.5 right there. 13.5. And then 1, 2, 3 is right here at 7.5. And basically what we're saying is that between minus 3 below the mean and plus 3 above the mean, the MAD was equal to 3. So that means most of my data should lie between 7.5 and 13.5. Let me just double check myself. 7.5, 13.5. Yes. So what it's saying is the mean is 10.5, and most of your data will lie between 3 units above or below the mean, which turns out to be 7.5 on the low side, which is below the mean 3 units, and 13.5, which is 3 units above the mean. So we're now really getting into the details of studying data. When you have a large amount of data, you can't write all the data down, and you can in a computer, but in real life, you're not going to remember all the data. We're not computers. So what we have to do is boil the data down to a couple of things we can understand. And the 2 most important things to understand about a set of data is what is its center value and how much spread does it have, plus or minus, about the mean. So we calculate the mean first, right, to figure out where the center point of the data is, and then we go through point by point and subtract each of these points minus the mean, and then the ones below end up giving us negative numbers because they're below the mean, but we take the absolute value of everything, so we get rid of any signs, so we know how far away this is from the mean and this is from the mean with all of positive numbers, and then we take all those numbers and just add them up and divide so that we average them, and we get something called the mean absolute deviation. That most of the data will, in this case, lie between plus or minus 3 units above and below the mean. In this case, plus or minus 2 units above and below the mean. That's what the MAD is. Then there's another way, totally separate, that's used in some other applications called the standard deviation that's very closely related. Instead of just averaging these deviations, first we square them. So we square them up and we add them up because we're basically going to average them. So we square them and we add them, and then we divide, just like we're basically averaging the squares. But then when we get the answer, we have to take the square root because in the process of squaring them, we kind of changed the meaning of what the numbers were. So we undid that by taking the square root of the final answer. The standard deviation should always be pretty close to the MAD, and it has a similar meaning. Plus or minus that many units above and below the mean is where most of your data will be. So solve these yourself. Very easy to make mistakes. It really is, because you have so many points, you have to subtract, you have to add, you have to divide. You can make a lot of mistakes. I make a lot of mistakes. Practice them. And then follow me on to part 2. We'll get a little more practice with the mean absolute deviation.